Hi guys. It's the waiting room right there. How you doing? Hope you guys had a good weekend. Is everybody all ready? Right. Math. Okay, hang on a sec. I'm gonna start keep admitting people here. There. So, if you guys didn't see it already, I sent an announcement out last night. Give me a sec. Announcement out last night about how your test results are up online, including the grading. You should be able to see all of my comments on the grading. I'll go check Gradebook to make sure that you're able to access that. I don't know why that wouldn't work, but you know, sometimes Gradebook is weird. Let's see. Also, your homeworks are your graded homeworks are done up online too. And there's a new homework assignment that's due this Thursday. Okay, that will be chapter 3.5 through 4.2. So 3.5, 3.6 we'll do today. I think we'll probably be able to get through both of those chapters. They're small and they're really similar in terms of topic. And then 3.7, 3.9, and 4.2. Okay. And then we're going to have a quiz again on Thursday, right? So I'll set that window up again on Thursday, kind of like what we have been doing. And just as a reminder too, in case it seems like we've got a lot of these quizzes and tests, we do have some kind of an assessment every Thursday. So we either have a quiz or a test every Thursday. And just as a reminder too, we're going to drop the lowest quiz grade. Okay, so we're going to have multiple quizzes and multiple tests. We don't drop any test grades or anything. Keep that in mind. The homework is up for this, and also all the lecture notes, lecture examples are up. So you guys should be able to get those and print them out. So make sure you have 3.5 and 3.6 printed out. I'm going to those today. Okay. Let me get everybody in here. Okay. All right. So unless anybody has any quick questions about administrative stuff, I'm going to start talking about chapter 3.5.
Hi, Professor. I think you uploaded section 3.6 in the 3.7 slot by accident.
3 points. Is it? Oh, you mean the homework? The homework assignment?
The notes, like the lecture notes.
Oh, so is it actually the notes for 3.7 or 3.6?
So 3.6 and 3.7 both show 3.6, I believe.
Okay, but you have 3.6 and 3.5, so we can do today, right?
Yes.
Okay, great. So let me make a note and I'll check 3.7 and I'll fix that after our class today. Lecture notes. Chapter 3.7. So it's just 3.7. That's wrong. Okay. So I'll fix that then later today so that you guys can have that for tomorrow. Okay, good. All right. Let's see. I think we're all set. Great. If there's anything else, if you guys have any questions about your test, I'll try to scan in the solution set for the test and then post that online too, so you guys can have that to study from for the final exam. Each test, by the way, that we have is only going to be for that chunk of material that we've just covered between the last test, you know, and this current one. But the final exam will be cumulative for the whole semester. Okay, so keep that in mind. So I'll try to get up a copy of the solution set for the test so that you can have those to study from. All right. Okay, so let's go ahead and get started. So chapter 3.5. Called expected value. Okay, so expected value, let's talk about like what that means. We're going to talk today about both, if I can get this straight here. We're going to talk both about, oh, sorry, I hope you're not getting dizzy. Get this straight there. We're going to talk both about a continuous and discrete random variables when we talk about expected value. 3.6 is variance. We're going to do both continuous and discrete for those as well. So expected value is essentially our mean. Okay, but it's a weighted average. So we're going to call it a weighted sum, a weighted average. Hang on a sec. Just admit people into our group here. Okay. A weighted sum, a weighted average, sorry, average of the possible values a random variable can take, and it's weighted by its probability. So we have our say in our discrete distribution, right, we have x could be equal to k, you know, whatever k is. K could be 0, 1, 2, 3, very finite set or countably infinite set, right? And so what we're going to do is we have each k values associated with a particular probability, okay? And we're going to multiply, we're going to weight that k value with its probability, and we're going to sum these up. And it's going to give us an idea about what our overall distribution leans towards. What's the expected value? What's our mean? So the expected value we call E of x, where x is typically our random variable. It could be E of y if that's our random variable as well. So E of x, but it's also mu, okay, our Greek letter mu, which stands for our mean, okay, of our distribution. So let me write this down too. Let's see, do it right here. So each value, each k value is weighted by its associated probability. Okay, we're going to see what this means as we go through and do things. So let me just talk about what it means to sum things up and to get this value, this expected value for discrete as well as for continuous. Okay, so if I've got discrete random variables, okay, what that means is I'm going to say my mu sub x, which is just another way of saying what's my mean for this random variable x. Hang on just a sec. I get this. There's a lag, isn't it? Okay, so my mean for this random variable x is going to equal to a particular x value. This is my k, my particular k value, what we've been typically calling that, and the probability that's associated with that value, plus my next x value. This is what my random variable x could take on, times, oops, sorry, this is a 2, times the probability that's associated with that. And I'm just going to keep summing those up until I get to the end, right? Where I have, basically I start off with 1 or whatever my x of 1 value, and I go all the way up through all the different possibilities that I have. I'm going to sum them all up, okay? And then we're going to write that in summation notation. So this is saying I equals 1 to k, x of I, p sub I, and that's going to equal to our expected value, okay? That's for our discrete random variable, okay? Our continuous random variable, it's also a sum, okay? But with a continuous random variable, when we talk about a sum, we're talking about integration, okay? So I'm taking a look at our probability density function, right, which is our f sub big X, right? F of our big random variable could take on any particular value of X. So we're going to use this, okay, to calculate what our expected value is. So our expected value, which is also our mean, we're going to integrate over our whole, basically the whole space where our probability distribution function is defined. For now, I'm just going to write minus infinity to positive infinity, so all real numbers, our whole sample space, x times f of x dx, okay? And this is going to give us our expected value for a continuous random variable. We're going to sum up all these possible values. So this is our x, basically our random variable x can take on a little x value, okay? And it's going to be associated with the particular probability at that x value, okay? And I'm going to sum up all of these things over our whole sample space. We're going to do a bunch of examples, both for discrete and continuous, so you can see what these things look like, okay? So essentially, so this is just basically a good summary of what we're trying to do here. So we can take a look at this and think about it as sort of a, like a long run average of the random variable. It's our expected average over many observations. What do I mean by many is kind of a subjective term. We're actually going to get into a discussion of how many observations do we have to have before we have a fairly high degree of confidence in what we're actually looking at. Okay, so right now I'm just going to say many, but note that as we progress along in this class, we're going to actually be able to define exactly what many means, okay? So let's talk about an example. I'm pulling out my example sheet for 3.5, and I'm going to do example number 1. So on example number 1, give me a sec. On example number 1, we've got this game. It's a gambling game, okay? Which means that I'm going to lose $1, right, with a probability of 0.3. I can break even, which means it's 0. I don't lose anything, I don't gain anything, so the amount that I get is 0, with a probability of 0.4. I can win $3 with a probability of 0.2, and I can win $10 with a probability of 0.1, okay? So this game looks like it's really biased towards just kind of breaking even, right? Because I mean, the highest probability is that I'm winning 0, okay? But the losing has a higher probability than winning $3 or winning $10, okay? All right, so this is our outcome. These are the associated probabilities, right, for each basically play that we're doing. We're not even talking about what the game is itself, okay, but we're just talking about essentially how we're summing up the outcomes and the associated probabilities. So now we want to find out what's the expected outcome on this particular gambling game, okay, which means that I can look at my mean outcome is what I'm thinking about, okay. So I'm going to think about my mu. My expected value, I'll call this my expected value, is my mean outcome. So I'm going to say I'm going to lose $1, right? So I'm going to put 1.00, so even though it's money, 1.00, I'm losing $1, and that's associated with a probability of 0.3. I'm going to add that to, I'm going to gain $0 with a probability of 0.4. Okay, I'm going to gain $3 with a probability of 0.2. And I'm going to gain $10 with a probability of 0.1. When you're summing these things up, you can just write 1, 3, 10. You don't have to write 1.00. I'm doing that so that you know that it's actually money, right? I didn't put the dollar sign in. Okay, but we're going to multiply it through, and we're going to add everything up. And we're going to get, basically our expected value is $1.30, okay? Which, so in the long run, as the player plays this game many times, okay, it plays, you know, you have these different outcomes for each play that you're playing, okay, they can be expected to win $1.30, okay, for every dollar that they bet. So it's actually pretty good odds, okay. Let's write that down. In the long run, the player can expect to win, oops, $1.30 by playing. Pretty much anything in the positive zone on a gambling game is benefiting the player. Anything in the negative zone is going to benefit the house. This is $1.30. Doesn't look like it. Okay, so these I'm going to just write. These are good odds because they're positive. You're going to take home some money. Okay. Okay. So example 2. I'm just going to scroll that up just a little bit so you can still keep typing it if you need it. All right. So example 2 is a roulette game. Okay, so we've been kind of talking about roulette. Roulette is a great, you know, game of probability. So on a roulette wheel, right, we've got 38 numbers on that wheel, right? I have 2, 0, 0, 0 as one block, 0 as another block, and then 1 through 36. So we have 38 numbers total, okay? We're going to define the odd numbers as 1, 3, 5, all the way up to 35. Then I'm going to define the even numbers as 2, 4, 6, all the way up to 36. So note that we're not counting the zeros as even numbers, okay? So the game, in this, how we're defining it here, is you're going to win $1 if you land on an odd number, and you're going to lose $1 if you land on an even number. So what are the expected winnings? Okay, so I'm going to say my x, my random variable x, right, I'm going to define my random variable x as the winnings that we have. X is our random variable, and they're representing our winnings. Okay, we're going to say x is going to equal to 1 if we land on, if an odd number comes up, or, you know, as we spin it, if our ball lands on that. We're going to say x is equal to -1 if it's not odd, okay? Because basically you're only winning, right, if you get a 1. Now technically it's true that if I get, we only said here you're going to get an even number, you lose $1 if you land on an even number, but we're basically going to count our zeros as part of that, okay, in terms of our probabilities that we're going to lose if we don't land on an odd number. technically speaking, I could probably set my zeros as a zero sum, okay? But in this case, I'm actually going to lump it into my even numbers, even though I said I wasn't going to. All right, so my probability of my random variable x, where is equal to 1, which is a way of saying that the probability that x is equal to 1, I'm just writing it in different ways so that you can see how the nomenclature is going to be, I've got 18 out of 38, right? I have 18 odd numbers. I have 38 total. Okay, so this is 9 out of 19 to win. Probability that x is equal to -1, that our random variable takes on the value -1, is going to be 20 out of 38, okay, which is 10 out of 19. So we're going to lose. We have a higher probability of losing, right? 10 out of 19. So my expected winnings right, which is our E of x, because x is our random variable for our winnings. Our expected winnings, right, I'm going to sum up, I'm going to weight this sum. So I'm going to win $1 if I land on an odd number, 9 out of 19, and I'm going to lose $1 if I land on not odd, 10 out of 19. Okay, and I'm going to sum those up, multiply through and sum them up. I'm going to get, basically, once I divide everything out, I'm going to get minus 0.053, okay, which is roughly 5-cent loss, okay, is our expected value. Okay, you would write actually your E of x is equal to minus 0.053, but in terms of money, what we're talking about is we're going to lose 5 cents, okay, in terms of how we're thinking about our game. Okay, but all we did was basically take our what we think our random variable is going to be, 1 or -1, and we're going to weight it by its associated probabilities. Okay, right? Okay, so let's talk about example 3. Put this down here in the view. Okay, so example 3 says, x is our binomial random variable. So remember, we talked before about binomial random variables. Oops, sorry. Get this straight. Okay, so we talked about our binomial, how we're going to set up our binomial probabilities. But here we're given p, our probability, and n. Okay, what n could possibly be, the number of items that we're basically operating with. We want to know what's our expected value. Okay, so now if I've got this, remember, so probability that x, my random variable x, can equal to k, is equal to, I'm going to write it like this, to probability that x is equal to k, right? These are just different ways of writing it. We're going to say our n, 3 choose k, times our probability, 5/9 to the k, okay, and this is 1 minus, this is our q, 1 minus 5/9 to the 3 minus k. Remember, this is our binomial probability, our binomial distribution here, okay? And in this case, k can be 0, 1, 2, or 3. Okay, so I basically have to take a look at my E of x is going to be the sum, right, for all these different k values. Okay, so I'm going to write it in summation notation first. K equals 0 to 3. K times the probability. Okay, so this is what my random variable could take on this value, times the probability associated with the random variable taking on that value. Okay, so now we're just going to sum these up. I'm going to plug it in also in summation notation 0 to 3. I'm going to plug in this part right here. It's just going to be k times 3 choose k, 5/9 to the k, 4/9 to the 3 minus k. Okay, so let's sum that up so you can see what this looks like. So when k equals 0, okay, k, I'm going to go 3 choose k, 5/9 to the 0, 4/9 to the 3, okay, and I multiply everything through, and I'm just going to get 64/729, okay, plus I'm looping around through my summation here. K can equal to 1, okay, my next one, 3 choose 1 times 5/9 to the 1 times 4/9 to the 2, okay, what that's going to equal to is 240/729, plus k can equal to 2. This is going to be 3 choose 2, 5/9 squared, 4/9 to the 1, okay, and that's equal to 300, 729, plus now k is equal to 3, okay? So this is going to be 3 choose 3, 5 ninths to the 3, 4 ninths to the 0. This is equal to 125, 729, like that, okay? So you're going to multiply through, this is 0 times that, 1 times this, 2 times this, 3 times that. Multiply everything through first and then sum it up, okay? And what I get at the end is 729, sorry, move this up so you can see. Okay. Which when I simplify it, I get 5/3, okay? That's my expected value. This is expected value. Now, I'm going to rewrite 5/3 just slightly so that you can see what we're doing. So 5/3 is equal to 3 times 5 ninths. Now, why would I do that? Because I want to call your attention to what this looks like. 3 is my n value. 5 ninths is the p value, right? And this is our expected value, okay? Let me just, I'll put a box around this here, and then I'm going to put a box around this here. I'm going to go back to our notes so that I can actually tell you what I'm doing here. Okay? Give you guys a second to finish writing that. Okay, so why did I do this? I did it because I wanted to call your attention to the fact that if x, our random variable x, is a binomial random variable, which means it's a random variable, but it has a binomial probability distribution underneath it, binomial random variable with parameters n and p, right? The number of things that we're selecting, and then p, the probability. Then our expected value is equal to n times p. Okay. Which we just saw in the example, that's why I was moving it apart. And I'll post these examples again, the solutions to it online later today. Okay, so let's talk about example 4. It's a little lag here on my computer. So example 4, we have, there we go, great. We have a bucket that has 9 chips, right? 9 chips total. We have 5 red chips and 4 white chips, and 3 chips are drawn at random without replacement. So when we're taking these things without replacement, we have to be thinking without replacement means it's going to be a hypergeometric distribution. Okay, that's this without replacement means hypergeometric distribution. I'm running out of space here, which is why I'm not writing it out. Okay, so our random variable x is our number of red chips. We want to find the expected value of x. So what's our expected value of number of red chips that we can pull out when we're taking 3 chips out without replacement? Okay. Okay, so let's think about that. So hypergeometric, I'm just going to write down our hypergeometric distribution again, probabilities. This is no replacement. Okay, so hypergeometric means I'm going to go the probability that x is equal to k, okay, which is, I can write it like this. Okay, remember, it looks like I've got 5, choose k, right? Because I've got 5 red chips, and I'm taking 3 out, but x is our number of red chips, which is why we're defining that as the thing that we make predominant. 5, choose k, all over 4, what's 5, like 9 minus 5, so 4, choose 3 minus k. So we're going to choose, the rest of them are going to be white chips, right? And then total, 9, choose 3, okay? And we're going to specify that k can equal, if we're only choosing 3 chips, I can have 0 red chips, 1 red chip, 2 red chips, or 3 red chips in when I pull out these 3 without replacement. Okay, so now when I go to work this through, right, my expected value is going to look like a sum from k equals 0 to 3 k times the probability associated with that particular k value. Okay, so it's going to look like, let's see, I'm running out of space here. Let's do this. So it's going to look like I'm going to sum up k equals 0 to 3. K times, I'm going to substitute, this is my probability in for my probability here. So 5 choose k, 4 choose 3 minus k, all over 9 choose 3. Okay, and this is going to look like, I'm going to go 0. I did all this out, multiplying it all the way through, so I'm just going to say 0. When k equals 0, I'm going to get 4 over 84. So that's 5 choose 0, 4 choose 3, all over 9 choose 3. We get 4 over 84 plus 1 times 30 over 84. I'm giving you these numbers. You can work it through if you want to prove to yourself, you know, that where these things come from. So this is 5 choose 1, 4 choose 2, over 9 choose 3, plus 2, 40 over 84. That's when k equals 2. K equals 3, I get 10 over 84. Okay, I sum them all up. They're weighted. Each k is weighted by its particular probability. And I'm going to get, my total thing is 5 choose 3. Okay. Well, there's a way to summarize our hypergeometric distribution as well in terms of expected value. I'll give you guys that in just a second and make sure that you're done writing it down. Okay, but we're using our probability distribution function, okay? Sometimes we have to define that, like if we know it's hypergeometric, I'm going to use it. If I know it's binomial, I'm going to use the binomial distribution. When we get into the continuous in just a moment, you'll start to see we're going to use our continuous distribution functions to help us figure out what our expected value is. Okay, so let's talk about hypergeometrics. We're going to generalize. Okay. Put this down so you can see. So if our random variable x is a hypergeometric random variable, which means that it has a hypergeometric probability mass function associated with it. And we're going to say with parameters, right? I need the number of red balls, the number of white balls, and the total n, okay? And then, so this is red balls, white balls, and sample size, okay? Then an x is, our random variable x is the number, the number of red balls that we want to pull out, okay? Then our expected value is going to equal to r times n all over r plus w. Okay, so that's summing it up for hypergeometric. Most often you're going to be seeing the binomial, okay? Binomial random variables, binomial distributions make up the bulk of what we're talking about in the statistics portion, because we tend to do, in real life, we tend to do binomial experiments. We say binomial experiments because we do trials, independent trials, where we're measuring success or failure. The outcome is one or the other. So it's a binomial result. So we tend to think about our underlying data, okay, as coming from a binomial distribution. So this one is the one that you really want to be thinking about. I'm just giving you also a shortcut for the hypergeometric. You can absolutely do it all the way out like we've just been doing too, but you now also know some shortcuts for it as well. Okay. So let's think just for a moment. We'll remember, we're going to talk about continuous random variables now. So when I think about continuous random variables, remember our expected value, okay? Our expected value is our mean. We'll keep reminding ourselves of that. And we're integrating over some interval, okay? We're going to go x times f of x dx, where f of x is our probability density function. Okay, that's associated with this particular random variable, okay? A to B typically stands for the bounds over which our probability density function is defined. You remember when we first started talking about our probability density functions with continuous random variables last week, we said it was this function and it was defined between, you know, x is equal to 0 to x is equal to 1, or x is equal to 0, x is equal to 3. That's what defines it. Okay, remember, the sum total of all of our probabilities has to sum up to 1. So that's where we get the bounds of this, okay? Because this is a function right here, right? We want to make sure that the total probabilities within that are going to sum up to 1, okay? So a to b, x times f of x dx gives us our expected value. Okay, if this looks familiar to some of the things you did in Calculus 2, it's true. We're going to kind of talk about this at the end. I think it's at the end of chapter 3.6. We're going to kind of sum up, like, you know, what this means in terms of other names. Okay, so continuous random variables. So let's talk about example 5. It's using a continuous random variable. So we've got x is our continuous random variable. Its associated probability density function is 3x squared, and that's defined between 0 and 1. Okay, I want to know what's our expected value. What's our mean for this? Okay, so I'm going to look at it, and I'm going to say my expected value. I'm going to integrate over my range of values that define this PDF, 0 to 1, and I'm going to say x times 3x squared dx. Okay, x times my function, my probability distribution function, integrated over the bounds that make it a probability distribution function. So this makes it 0 to 1, 3x cubed dx. I'm just going to do the power rule on it, which is going to give me 3 over 4 x to the 4th. I'm going to evaluate that from 0 to 1. Okay. Once I plug in and I do the fundamental theorem of calculus, I'm going to get my expected value is equal to 3/4. Okay. That's the mean, my expected value for this particular distribution here. Okay. All right. Okay. We're going to roll through a bunch of examples so you can see how these things work. So example 6 says, given that x is a continuous random variable, it has an associated probability distribution density function, x e to the minus x, and that's defined between 0 and infinity. Okay, so already we're starting to think I'm going to have to do an improper integral on here, because I've got 0 to infinity that I need to think about. Okay, so now I want to find out what's my e to the x. Okay, so remember our e to the x, right? I'm going to go from 0 to infinity. I'm going to multiply x times my probability distribution density function, x e to the minus x dx. Okay, which is going to give me 0 to infinity x squared e to the minus x dx. Okay, which means I've got an improper integral here. So I'm going to rewrite that first as a limit. So I'm going to go the limit as b goes to infinity, 0 to b, x squared e to the minus x dx. All right, I can't just integrate this however I feel like, right? I've got a function here and a function here, okay, which means I have to employ the whole process called integration by parts. Okay, so let's remember integration by parts is u times v minus the integral of v times du. Okay, and I have to assign what values are of u and dv. Okay, and I'm going to take a look here. So when I do this, so first I'm going to just, while I do the integration by parts, I'm going to drop the limit integral because I've got the integration by parts to worry about. Then I'll put the limit back on when I'm done. Okay, so the integration by parts. So the first thing I'll do is I'll assign u equals x squared, which makes my du equal to 2x dx. My dv I'll assign as e to the minus x, which means I need to integrate both pieces. So it's going to give me a v of minus e to the minus x. Okay, and I'm going to plug those into my uv minus v du format here. So I'm going to get x squared minus e to the minus x. I put multiplication on it just so that I keep myself honest that this isn't a subtraction. It's things like you're not going to do it when you're doing your homework, but when you get on an exam and you're going fast and you're a little nervous, you want to make sure that you remember you're multiplying and not subtracting. This would be minus a minus, that becomes a plus, e to the minus x times 2x dx. Okay, so this would be minus a minus. Okay, that's where we get the plus from. Okay, so now the 2 I can take out. So this becomes plus 2. Let's make this x e to the minus x dx. Well, again, I have two functions being multiplied together, so I have to do integration by parts again. Okay, so I'm going to just write down really quickly, u equals x this time. My du is equal to just simply dx. My dv, again, is e to the minus x. I'm going to integrate this to get v equals minus e to the minus x. So I'm going to plug this all in. Don't forget we have a 2 multiplying it, and I've got this bit here that I need to think about. So let's bring this out over here. So I've got minus x squared e to the minus x, that was from before, plus 2. I'm going to put a bracket because I'm doing uv minus v du. So again, I'm going to go x e to the minus x. This is minus a minus e to the minus x dx. Now I can just integrate this normally without having to do integration by parts again. Okay, so what I'm going to get at the end is minus x squared e to the minus x plus 2. Let's see, I'm sorry, this is going to be, let's do this. Oh, sorry. X e to the minus x, right? And this is going to give me minus e to the minus x. Okay, I just integrated that. I haven't distributed the 2. I started to think about it and I changed my mind. Okay, so now I'm going to put the limit back because I'm done integrating. So I'm going to put this limit back. So I'm going to say the limit is b goes to infinity. And everywhere I see an e to the minus x, I'm going to put it in the denominator to keep myself honest about how I evaluate this b value. Okay, so this is going to become minus x squared all over e to the x minus 2x all over e to the x. Let's see, minus 1 all over e to the minus, e to the x. And we're going to evaluate that from 0 to b. Okay. And I think there should be a 2 here, right? 2 right there. Because I'm distributing the 2 to both. Okay, so now when I plug in b, right, this is e to the b. b is approaching infinity. Infinity is in the denominator on each of these here. So this is going to look like, I'm going to go minus, let's see, b squared all over e to the b, minus 2b all over e to the b, minus 2 all over e to the b here. And I'm going to say minus 0 minus 0 minus 2e to the 0. Okay, actually plugging it in. These terms here, I'll go to 0. My exponent is going to outpace my b squared. Okay, so I'm not worried about having infinity squared all over e to the b. Okay, I could do L'Hopital. L'Hopital's is how you would actually prove this, but in reality, you don't have to do L'Hopital's at this point if you recognize that exponentials are going to outstrip. This one's going to reach infinity before this one does. So all these terms go to infinity, and I'm left with, basically at the end, minus times minus, this is going to be 2, which is equal to our expected value. Seems a little anticlimactic after all the work that we just did. Okay, but it's a good review of the calculus, okay, that we need to keep in mind that we're going to be starting to pull in so that we can evaluate these functions. Okay, and I'll leave this up here for you guys to think about and finish writing, and then we'll move on. Okay, right. So let me talk about a concept. I'm going to come back to this concept multiple times. It's called our central tendency. Okay, so the central tendency is that most values of our probability distribution function, and I'll put both, this is our discrete and our continuous, are going to focus near our expected value. Okay. Okay. So with the discrete probability mass function, it's going to look something like this. Okay, so most of my values are here. Okay, so this is our, this value here is our mu of x. Okay, then our continuous probability distribution function is going to look like I didn't draw that, should be symmetric, possibly. U of X. Okay, so this is basically saying that most of our values are going to be really, really close. They're going to be centering on our mean. Okay, this is called our central tendency. You'll see this also. There's a concept called the law of large numbers, right? Which is that as I keep accruing more and more and more samples, right? As I get more and more, if I have a survey, if I only survey like a handful of people, maybe my results aren't so robust. But if I survey 100 people or 1,000 or 1,000,000 people, okay, my values, the types of answers that I get are going to basically center, okay, along the mean, along the expected value. Okay, you see this distribution when you start to do sampling, especially if you're polling people on a yes/no, success/fail type of a question. Okay, but we're going to come back to this. But what can happen with our mean, right, with any kind of distribution like this, our mean is a weighted average, right? Because our anticipated values, our k, x equals k, are going to be weighted by the probability. So the weights here, right, these k values can be skewed by values that are extreme. At extremes. So often a median, the median value, the median is a better measure, right? Because it basically kind of tosses out the extreme values, okay? And then it weights things more close to the central area. So it's going to divide, we'll kind of write this in parlance. So divide our area under a probability distribution. It's a probability density or mass function into 2 equal areas, okay? Right? So basically, what that's going to look like is, for our discrete random variable, we'll break this up into both discrete and continuous random variable. Okay, the median is the point for which, we call median is our m. Median is the point for which the probability that our random variable x is less than m is equal to the probability that our random variable x is greater than m. Okay, that the probability is basically equal out on either side. Okay, and we can say if the probability that x is less than or equal to m is equal to 0.5, and the probability that x is greater than or equal to m prime, I'll call it m prime, is equal to 0.5, so that my balancing point, okay, is equal on both sides, then our median is simply the arithmetic average of these two m values. So m plus m prime divided by 2, because it's already been split in half. Okay, this point is already kind of defined as our halfway point here. So now our continuous random variable, we're going to do this again, but continuous, we have to think about them out slightly differently. Our continuous random variable is going to look like this. I've got minus infinity to m, right? So I've got my whole sample space essentially. We say minus infinity because, you know, we don't know what our lower bounds is. So my whole sample space up to the median point, right? This is my probability distribution. Dx is equal to 0.5. So what's the point at which, what's my x value, what's my m point at which my probability distribution is going to be split into 2, 0.5. Because remember, if I were to sum this up, minus infinity or positive infinity, sum up the whole thing, it should be equal to 1, right? So I'm saying at which point does this probability get cut in half? Okay. Okay. So just some other things to think about too before we go on to examples here. Can you see that? I'm gonna make sure you guys can see. So if
what was the continuous random variable for the mean?
The continuous random variable, median, you mean like right here? So we're gonna find,
yeah, the mean.
Yeah, we're gonna do an example on as to how we actually solve for that. It's basically at what point you can think about, like I've got this function, say for example, and I'm gonna sum up between a to b, right? But instead of going from a to b, because if I did sum across that whole PDF, essentially I would be getting a value, a sum of equal to 1. So I'm going to go, you know, a to m. I don't know what m is, but I know that when I sum this up, it's going to equal to 0.5. I'm cutting my distribution function in half, right? And then I'm going to have to solve for that. And we're going to do an example so that you can see how we solve for this, given that it's actually within the bounds of integration.
Okay.
Yep. So if our random variable, if the random variable's PDF is symmetric, which is going to happen when we get into like our normal distribution later, this in the second half of the class. If it's symmetric, then our mean is equal to our median. And that's an important concept which we'll exploit in the second half of the class when we talk about statistics and using a probability distribution function that's based on what we call a normal curve. Okay, but I'm getting ahead of myself. Okay, so then if I say if my probability density function, or a mass function, if it's not symmetric, right? So like, for example, if we have big outliers, okay, or the shape of it is inherently not symmetric, which we'll do an example in just a minute where it's not symmetric at all. The difference between our mean, our expected value, and our median can be big. Can be big. So then oftentimes our median is a better measure of our data. Okay, so maybe we want to find out what the median is because it's going to give us a better marker for things. Okay. Which is going to bring us to example 7, which we're going to talk about. This is a decreasing exponential probability density function. So the decreasing exponential is pretty heavily weighted, right? It's got a really high front end, and it basically asymptotes off at 0. So let's draw this out. So example 7, okay, we've got this. If a light bulb has an average lifetime of 1,000 hours before failure, is it reasonable to assume that each bulb that we buy will last for 1,000 hours?
Can you go back for 1 sec?
You bet.
Thank you.
Yep, no problem. Okay, so if we're told, because we often buy products and they say this, you know, these LED light bulbs will last for 10,000 hours. We want to know, so does that mean that each bulb that we have, what's the probability that each bulb that we buy will last for that time that they're saying, right? So we've got this continuous probability density function, f of y, and that's going to model the length of time y that the bulb is going to work, okay? And we're given this. So we've got some coefficient 0.0001 e to the minus 0.00. Do I supposed to have another 0 in there? Oh, no. Sorry, I added an extra 0. There should only be 2 zeros. So 0. Let me get rid of this 0 here. 0.001 e to the minus 0.001 y. Looks like I typed in an extra 0 by accident. Okay, so y is positive. So let me just sketch out. So it's a decreasing exponential, right? Which is going to look like this. So you can see when you graph, just kind of to get a feeling for what you're looking at, right? So this is not symmetric at all, right? And this is our random variable y. This is our time that it's going to work. And this is our probability, okay, that's associated with that time. So at the beginning, right, when I first install the bulb, I have a really high probability that it's going to work fine. As I progress along in time, in hours, right, my probability that it's going to work decreases, and it decreases fairly rapidly, right? This is a pretty steep curve here. Okay, so what we want to do is find the median lifetime for the bulb. So we want to do median, right? Because this is a very lopsided, very asymmetric density function, right? So the median is going to be a better marker. So the median bulb, so I'm going to go from 0 to m. I'm going to take my distribution density function, 0.001 0.01 e to the minus 0.001 y dy, and I want to set it equal to 0.5. 0.5 is my halfway mark. Right, I'm splitting, right? At what point, where is M along this value here, right? I'm just gonna put a little marker here. So where is M, right? I need to know exactly what that value is. Where's M, right? That's gonna split this distribution, this density function, into two pieces, okay? Because if I were to sum the whole thing up 0 to infinity, I would get it equal to 1. Now I want to find out where's the halfway mark. Okay, I'm going to skip the integration on this. Okay, you guys can do the integration offline, confirm that you know, everything was done correctly. But basically, once I integrate it and I plug in, I do my fundamental theorem of calculus from 0 to m, my evaluation, I'm going to get 1 minus e to the minus 0.001 m, and that's equal to 0.5. Okay, so I integrated. This is equal to 0.5. I get 1 minus e to the minus 0.001 m, and that's equal to 0.5. Okay, now I need to solve for m. So the first thing I'm going to do is I'm going to subtract 1, right? And I'm going to divide by negative, because I want to make this positive. So I'm going to make this e to the minus 0.001 m, that's an e, is equal to 0.5. Okay, now the m value that I want is in my exponent. Okay, so to get it out of my exponent, I'm going to take the natural log of both sides of the equation. Okay, and that's going to give me minus 0.001 m is equal to the natural log of 0.5. Okay, this is just a number. I'm going to leave it like that for now. I'm going to divide both sides by minus 0.001. I'm going to find m is equal to 693.1. And we're talking about things in hours. Okay, so what does this mean? What, like, you know, what's going on here? So with our median, what this means is that we have a 50% chance that the bulb that we buy will last only 693.1 hours instead of 1,000 hours. Right? We were promised that all these bulbs, the average lifetime for a bulb was 1,000 hours, right? But is it really, like, this particular bulb that I'm buying, what's the median lifetime of our bulbs? Okay, so our median lifetime is 693 hours, which is still actually not so bad. Okay, but we have a 50% chance that the bulb we buy will last only 693 hours. Okay, so then I could say that this m value, I'm just going to put here, this is 693.1, and that's in terms of hours. Okay. That's how we find our median. And we would use the median when our our underlying probability distribution is skewed like this, right? It's got a really sharp decrease in the value. Just so you know that the statistics part that we do in this class, the second half of the class, we're assuming we have a very symmetric curve, okay? So we're going to be, in our symmetric curves, our median and our mean are the same. Okay, so we're operating under that assumption that the median and the mean are the same when we have a symmetric curve. But depending on the data that you're gathering, we're going to talk in chapter 4.2, we have a different type of probability distribution we're going to introduce, okay? Certain types of data naturally fall under this other, it's called the Poisson, this is 4.2, type of distribution, okay? And then basically we'd need to analyze things according to that distribution function, okay? But a lot of the statistics that we do in the second half of the class are assuming I have a very symmetric curve where my mean and my median are the same. But it may end up that you have a distribution function that's not symmetric, and you'll need to know that a median is probably better to use than your mean, okay? So there we go. So that was chapter 3.5, okay? And I'll post the lecture examples later, so that you guys can have those online. And I'm going to get out my lecture examples for chapter 3.6, and then we're going to roll into that. And if we need to finish it tomorrow, then we will. Okay. So chapter 3.6 is similar, different, but it's a similar process. Chapter 3.6, it's related. It's called the variance. Okay, so we're going to talk about methods for how we calculate the variance. We're going to be teaching you these methods when we get into our probability and our statistics portion, we're going to be using mean and variance quite a bit, okay, but just so you know how things are being calculated behind the scenes. Okay, so the variance, we can typically call it sigma squared, okay, or we can call it the VAR of our random variable x, okay, just different ways of notating it. So the variance of a random variable is the spread or variability of the distribution. So we can tell a lot about the underlying data if we're given the mean and the variance, right? So the mean is going to tell me where's my central tendency, right? Is it all the values are kind of, you know, grouping around this one particular point? That's probably my mean, my expected value. The variance is going to tell me, right, if it's a highly variable data set, my spread of data is going to be fairly wide, okay? If the variance is pretty limited, right, there isn't that much variability in the data set, that means that most of my data points are going to be clustered very closely to the mean value, okay? So we'll talk, you know, graphically as we go, like, so you can kind of build up an intuition so that when you see a variance, or we'll talk also about it in terms of standard deviation as we go along. Variance and mean, okay, those are our two quantitative aspects to help us describe our data distribution, okay? So let's talk about how we calculate our variance for both discrete and continuous random variables. So first with discrete. Okay, so our discrete random variables, we want to calculate our variance for it. So we'll say x is our random variable, right? And we have an associated probability mass function. Right, and I'll call it p sub x of k. Okay, that's my probability mass function of my random variable x. Okay, now the variance of my random variable, I can calculate it as the expected value of x minus my mean squared, right? So I'm looking at basically, I've got the mean of this data, I've got each individual x, okay, for my values, what my random variable could take on. I want to know how far away, how close each individual value is from the mean, okay? So I'm doing this here. This is like saying I'm going to sum up all the possible values, all my k values, x of k minus my mean squared times the probabilities that are associated with that particular x of k, okay? There's a shortcut to calculating our variance, okay, that I often use. We're going to do, the shortcut is nice because it limits how much algebra you're doing so that you are less likely to make an algebraic mistake. And this is equal to e of x squared minus e of x quantity squared, okay? So this calculates my variance right here, okay? And we're actually going to go through examples on this here. And I'll just write this out here. So this is all k, x of k squared, px of k minus mu squared, okay, where mu is our expected value or our mean, okay? So this is for discrete random variables, our variance, and this is e of x squared minus e of x quantity squared, okay, our mean here. We're going to do the same thing for our continuous random variables. Let's see. Okay, for continuous random variables, only instead of summing things up with a summation, we're going to sum them up with an integral. Okay, so our we'll call y as our random variable, our continuous random variable, and it has a probability density function. Call it py of y, okay, which I'll call fy of y. These are just different ways of writing our probability density function associated with it. So I can say my variance for this continuous random variable, which is my sigma squared, and that's equal to e of y minus mu quantity squared, okay, Same type of idea that we did with the discrete, and that's equal to, I'm going to sum up over my whole space, minus infinity to positive infinity, y minus mu squared, and then my probability density function. Okay. I can employ the shortcut on this one too. We have y squared minus e of y quantity squared. Right, so we calculate the mean first and we square it, and then we subtract it from, right, our this e of y squared portion. And how this looks in integral form is like this. I'm going to go from minus infinity to positive infinity. I'm going to go y squared times my probability density function, dy, and I'm going to subtract out, right, I'm going to integrate, this is my mean, so minus infinity, positive infinity, oops, that's an infinity, y, f, y, dy, quantity squared. This is our u squared term right here. Okay. This is the portion whenever we're asked for the variance, we need to calculate the mean because we're going to use the mean squared as part of our calculations. Okay. As you know, we're integrating, right, from minus infinity to positive infinity. These are improper integrals. Okay. If any of these improper integrals diverges as a part of taking the limit process, that means our variance is not defined. Okay, so I'll say, let me just write that down. If integral diverges, right, because it's an improper integral diverges, then e of x squared or e of y squared, however, whoops, that's a y squared, however, whatever variable we're calling it, is not finite, which means that our variance is undefined. Just to keep a note on it. Hopefully, you know, when we're doing these calculations, it'll be defined, but you should know, right? It's possible, mathematically speaking, for our improper integral to diverge as we're evaluating it, okay, which means that our variance is going to be undefined. Okay. Okay. Give you guys a second to finish writing that, and then we'll talk about example 1 from 3.6. Okay. All right. Let me know if you need me to go back to that. Okay. So example 1 says we have a discrete random variable. This is x. Okay. And its associated probability mass function, which is given right here. Okay, so x can take on values of 0, 1, 2, or 3, and these are the associated probabilities for it. So we want to find the mean and the variance for this random variable here. Okay, so we'll do the variance with those two different methods we're talking about, and you'll see that the shortcut method is really nice, has a lot less algebra in it. Okay, so first let's calculate our mean. That's our expected value, and that means I'm going to sum up. So from k goes to 0 to 3. These are the values that my random variable can take on. X sub k, probability of x sub k. Oops, there we go. Okay, so all that means is I'm going to take my value of x and its associated probability, multiply it, add them together. 4 plus 2 times 3/8 plus 3 times 1/4. Okay, and in the end, I'm going to get 7/4, which is equal to 1.75. I don't care if you give me decimals or fractions, I can figure it out. But they're both correct. So that's our mean, okay, for this distribution here. That's our expected value, okay. So now to calculate the variance, okay, I'm going to do both methods. So I'm going to go e, x minus mu, quantity squared. And we're going to think about what that looks like. So I'm going to sum up k equals 0 to 3. I'm going to say x, each x minus the mean, square it times the probability associated with that particular x value. Okay, so it's going to look like this. I'm going to go 0 minus 1.75, right? This is our mean, and that's square it, and that's associated with the probability 1/8. Okay, plus we're going to do this for all of them. 1 minus 1.75 squared. Oops, and this is, sorry, 1/4. plus 2 minus 1.75 squared. The squaring actually makes sure that we have a positive number that we're working with. And this is 3/8 plus 3 minus 1.75 squared times 1/4. Okay, so I'm going to sum all these up, and I'm going to get it equal to 0.9375. Totally okay to do that method. This is our variance. Okay, we'll talk in a minute. If I want to talk about standard deviation, right, I'm going to take the square root of this. Right, so if I take the square root of that, I'm just going to get 0.97 as my standard deviation. We tend to think about things in terms of standard deviation, but variance is actually the metric that we use. But we'll talk about what these things look like calculus-wise as we progress along. Okay, so let's do the alternate method, the shortcut. Just so you can see both in action here. Okay, so my sigma squared is equal to e of x squared minus e of x quantity squared. Okay, and so what that's going to look like is, right, I'm going to go e of x squared. So that's going to be my x gets squared, so 0 squared times my probability, right, plus 1 squared times its probability, 4, plus 2 squared times its probability, 3/8, plus 3 squared times its probability. Okay, this gives me my e of x squared. So let's write this down. This is e of x squared here. That's what I'm calculating. Okay, so now when I do my e of x squared, I'm going to get, what did I get for that? Let's see, sorry, I guess I didn't sum it up. E of x squared minus e of x quantity squared. We already calculated e of x. Our e of x was right up here, 1.75. We need to square it. Okay, so I'm going to take this whole sum and I'm going to subtract off 1.75 quantity squared. Okay, when I do that, I'm going to get my total answer, my variance, is equal to 0.9375. It's the same thing. Okay. Personally, I like this alternate method better. It's easier to remember, e of x squared minus e of x quantity squared. Less algebra, I'm less likely to make a mistake. But where this comes from is we're taking each individual x value, right? And I'm subtracting it from my expected value, finding out how far away from our expected value, from our mean, it's going to be, okay? And then I'm multiplying that by the probability that's associated with that particular x value. So it's still a weighted sum, okay? But this is our shortcut here. It's a little bit easier to use, okay? I'll give you guys a chance to finish writing that. Like I said, I'll post these too. All right. I'm going to start scrolling up just a little bit. So example 2, we have a 6-sided die, okay? And the probability mass function, this is discrete probability mass function, right? It's a fair die. So it's a 6-sided die. So each face is 1 or 2 or 3 or 4, all the way up to 6. So the probability for any particular face showing up is 1/6, and it's 0 otherwise, okay? This is what we would call a uniform distribution, meaning that for all values of x, everything is equal to 1/6. So this is our x value. This is 1, oops, sorry, that's 1, 2, 3, all the way up to 6. Okay, so it's what we call a uniform distribution. It's completely flat. Okay, so we want to find out what are our expected value, our mean, and our variance. Okay, let's go ahead and calculate it. So our expected value is equal to, we're going to sum up k can equal 1 to 6. Okay, this is going to be x times its probability. Okay, and what I'm going to do is I'm just going to sum. So this is, I'm going to factor out, this is a 1/6, right? This is 1/6 times 1, 1/6 times 2, plus 1/6 times 3, plus 1/6. So I'm just going to factor out the 1/6, save myself some writing. 2 plus 3 plus 4 plus 5 plus 6. I'm going to sum up all of my possible fate. This is, right, my x times my probability, my x times my probability, and so on and so forth. Okay, which gives me 21/6, which is about 3.5. So that's my expected value. Okay. it's a uniform distribution, so it makes sense it's somewhere like around the middle. Okay. Oh. Okay, now let's talk about our variance of x. Okay, this is our sigma squared. So I'm going to do this method, e of x squared minus e of x, quantity squared. Okay, so I'm going to need this e of x, because I'm going to need to square it in a minute. So I'm going to calculate e of x squared. X squared is going to equal to, I'm going to sum up. K goes from 1 to 6, right? And this is going to be x squared times the associated probability. So I'm going to plug in these values again. So this is going to be my probability, 1/6, times each individual value that my random variable could take on, which is x squared this time. So 1 squared plus 2 squared plus 3 squared plus 4 squared, 5 squared plus 6 squared. Okay. And then this thing is going to equal to 91 over 6, which is roughly 15.16. Now that's just my e of x squared. Okay. To calculate my sigma squared, right, I have to do e of x squared minus e of x quantity squared. So I'm going to say 15.16 minus my mean, 3.5 squared. Okay. So I'm going to put this in. I'm going to get 2.916 as my variance. Okay. Just to note, my standard deviation, I take the square root, is equal to 1.707. Okay. Be careful, if you're asked for the variance, make sure you don't give the standard deviation by accident. Just to note also, while my mean can be negative, right, because the mean is going to depend on the underlying data, the variance is always positive. Okay. You should see that. I'm going to move this back up just a little bit here, just in our discrete case, and I'll come back to it in a minute. But remember how we calculated. This is each individual x value, its distance from the mean squared, right? So I should always have a positive value here. All my probabilities, individual probabilities are positive. I'm summing things up. So this should give you a clue. My variance must be positive. If you're doing the shortcut method, it's easy to make a mistake in your math, okay? And then to get like a negative number on your variance. If you get a negative number, you probably made some math mistake somewhere. Okay, maybe you swapped the two, you subtracted the wrong thing. Go back and check, okay, because that's a good reality check. Did you get a positive number here? Okay, because if you got a negative one, you made a math mistake somewhere. Okay. I'll give you guys a second, and then we'll go on to the next example. Okay. So example 3. Right, so we did this previous example, right, when we have 3x squared from 0 to 1, okay? So we're taking a look at our mean and whoops, sorry, you can see that, let me bring this down. Our mean and our variance for this, we did this example, we calculated the mean previously. Okay, so from before, let's see, we calculated our mean, right, was equal to 3/4, okay? That was the stuff that we calculated in the previous section. I'm just reusing this here so we can use it to calculate our variance. So now our sigma squared, variance of x, e of x squared minus e of x, quantity squared. So I need the mean in order to do this, but we're recycling it from before. Okay, so now to calculate this, I need to calculate, I'm going to do my e of x squared bit first. Okay, so my e of x squared, right, I'm going to calculate same bounds. So I'm going to go from 0 to 1, x squared, okay, times my probability density function, dx. Okay, x squared times 3x squared. I'm integrating from 0 to 1. That was the bounds that were given to me for this probability density function, which is equal to 3. This is going to be x squared times x squared, x to the 4th dx. I'm just doing the power rule on this one, which is going to give me 3/5, x to the 5th evaluated from 0 to 1. Once I plug in the numbers, I'm going to get 3/5. Now that's just e of x squared. Be careful, that's not your variance. It's just the first part of your variance calculation. So now my sigma squared, right, I'm going to plug things into here. So that's going to be 3/5 minus, I take my mean from before, 3/4. Don't forget to square it. Okay. Once I square it, I'm going to get 3/5 minus 9/16, and that's going to give me roughly 3/80, which is about 0.0375. And that's our sigma squared. Okay. I'll keep giving you the standard deviations too, if I have them. Okay, but watch out. If you're asked for the variance, make sure you're calculating that. Okay. Okay, so be careful, right? E of x squared minus E of x quantity squared, right? I'm plugging in x squared times my probability density function. Okay. Example 4, another continuous variable. This one we're using variable letters instead of actual numbers. So our distribution function looks like p plus 1 times x to the p, where p is some real number, and we're going to go from 0 to 1. P is any real number, okay, which could be a 3, it could be a 5, it could be whatever, okay, but we're integrating it accordingly, okay. So now I need to calculate my expected value and my variance given this, but remember p is not a variable, it's just a number, okay. So I'm going to think about that. So my expected value, right, would be x times my distribution function. So I'm going to go from 0 to 1, over which this is defined. I'm going to say x times my distribution, p plus 1, x to the p, dx. Okay, now remember, p plus 1 is just a constant term, right? So I can take that out of my integral. X times x to the p, right? These have the same base, so I can add their exponents. This becomes x to the p plus 1, okay? So this is x to the p plus 1 dx. P is just a number, right? So if p was 3, this is now x to the 4th. Okay, so I'm just going to be integrating that using the power rule. Okay, so when I go to integrate that, I'm going to get p plus 1, the constant that I had before, times x to the, I have to increase my exponent by 1, and then divide by my new exponent. Then I'm going to evaluate that from 0 to 1. So I plug in 0 to 1 into x, right? And I basically get p plus 1 over p plus 2 is my expected value. Okay. This is kind of more of a thought experiment, just that you get comfortable thinking about the process of things, as opposed to just having, you know, numbers that you're working with. Okay, so let's do variance. And we're going to use our shortcut method. So e of x squared minus e of x quantity squared. Okay, so now my e of x squared, I'm going to set it up just like I did before, where I integrate from 0 to 1, only now I'm multiplying by x squared, p plus 1, x to the p dx. So again, I'll take p plus 1 out of my integral, 0 to 1. Now I've got x squared times x to the p, which means I'm going to be looking at x to the p plus 2 as an exponent, dx. So again, I'm going to be using the power rule when I go to integrate this. Okay, so this is going to give me p plus 1 times x to the p plus 3, because I have to increase my exponent by 1, and then divide by my new exponent. I'm going to evaluate that from 0 to 1, and that's going to give me p plus 1 all over p plus 3, and that's equal to e to the x squared. Remember, that's not our variance, that's just the first half of the variance. So I'm going to plug that in to help me calculate the variance. Right, e to the x squared, e of x squared minus e of x squared. So e of x squared is equal to p plus 1 all over p plus 3 minus, I'm going to take my e of x from before, p plus 1 all over p plus 2, and I'm going to square it. And I'm going to leave it. I don't know what p is. I'm not going to worry about common denominators. I'm just going to leave it like that. This is the kind of thing, right, where maybe you're trying to model something, okay? You have a graph of your variance, and you can come up with a graph of your variance as a function of p. You know, what do I want my variance to look like? I want it to be small, I want it to be big. What kind of value of p is going to basically optimize this variance value here? But for now, we're just leaving it as in terms of p. Okay. So give you guys a chance to finish writing that before we talk about some properties. So I'm going to talk about some properties of our means and our variance. I'm going to put them up without proofs. I think your book actually goes into some detail about where these properties are coming from. Okay, I'll leave it to you to take a look at those. We're talking about how do we utilize these and how do we use it to analyze probabilities and distributions. So properties of means and variance. Okay, so I'm going to say my expected value, right? We've been talking about expected value of x, but let's say I'm going to multiply x by some real number a, and then maybe I'll even add like a value in there too. So I'm going to say a and b are, you know, real numbers. They're just constants. Okay. Now, if I do this, what's my expected value? Instead of just playing x, I'm going to multiply by x, I'm going to add b. We're going to do examples so you can see what this looks like. It's going to be a times my expected value plus b. So if I am multiplying something by my random variable, I'm going to change our mean by multiplying by that same constant, and I'm going to add b to it. Our variance of ax plus b, okay? The b doesn't change our variance at all, but the a gets shifted into our variance as a squared. So if I calculate, if I'm asked to do what's the variance of ax plus b, I'm going to calculate the variance of x, and I'm going to multiply it by a squared. Don't worry about the b. We're going to see it has no effect on our variance. It will on the mean, but not on our variance. That's property number one. Property number two is the mean of the sum of two random variables. We'll call them x and y, okay, is the sum of their means. Okay, so if I want to say the mean of x plus y is equal to the mean of x plus the mean of y, I'll write it out in math terms. And also this assumes, like much of the statistics that we're going to do, that x and y are independent. Okay, remember what that means in terms of probabilities and how these random variables interact with one another. Okay, now when I have the variance, if I've got the sum or the subtraction, the addition or subtraction, okay, of any of these random variables, this is going to be just the sum. Okay, I'm not going to be subtracting their variances. Okay, when I'm adding or subtracting, when I'm interacting these two random variables, okay, their variances are going to sum. I'm increasing the variance, okay, by having these two independent random variables interact with one another. So it doesn't matter if they're adding or subtracting, my variance is just addition, okay? Whereas the means here are going to be add. It would be like add and subtract for that. Okay, so let's go through some examples so you can see how this actually holds together. All right, so this is a discrete example 5. We'll see how we're adding things together. We're using a discrete value first, a discrete random variable first. So we've got this.
Can you go back for one quick?
Yeah, you bet. I can't see if people are still writing, so I have no idea. It's good that you tell me.
Oh, thank you.
All right, so you've got this casino gambling game. They make great ways to analyze stuff. The outcomes and the probabilities are like this. We lose $1 with a probability of 0.3. We break even, 0.4. We gain $3. We gain $5. We want to find out what's the mean and the variance. Okay, so we're going to do this out. So my expected value, which I'll write interchangeably as these two as our mean, is -1 times 0.3 plus 0 times 0.4 plus 3 times 0.2 plus 5 times 0.1. Okay. So I'm going to weight these sums. I'm going to add them all up. And I'm going to get my mean is equal to 0.80. Guess your mean is like 80 cents. Okay. Now our variance of x, remember this is equal to e of x squared minus e of x quantity squared. So let's calculate e of x squared, okay, and we'll plug things in. So e of x squared, so I'm going to go Okay, so this is minus 1 squared, 0.3, plus 0 squared, 0.4, plus 3 squared, 0.2, plus 5 squared, 0.1. Okay, and that's equal to 4.6, and I'm going to subtract out 0.8 squared. This is our mean squared. Sorry, that's a 2. 4.6 minus 0.8 squared. And when I multiply all that out, I get my variance is equal to 3.96. Okay, that's our baseline thing. So now we're going to change things a little bit. So the casino wants to change the outcomes, right? They think maybe it benefits the players too much, right? We have a positive mean value, so maybe it benefits people. So we're going to subtract $1 from each prize, right? So we're going to keep the probabilities the same. So now you can lose $2 with the probability of 3, lose $1 with a probability of 0.4. You gain $2 and you gain, whoops, that should be not 400, it should be $4 with a probability of 0.1. Okay. So now let's calculate, we're going to change. So basically all we did was we took our, all of our values, our X random variable, and we subtracted a value from it. We're going to see what happens here in terms of our mean and our variance. So our E sub X, our mean, okay, we're going to do the same thing that we did before. So minus 2, 0.3, plus minus 1, 0.4, plus 2, 0.2, plus 4, 0.1. Okay, multiply it out, sum it all up. I'm going to find that my mean now, my expected value, is negative 20 cents. So by subtracting 1 from each payout, right, they've changed the odds now from in favor of the player to in favor of the casino, right? Negative means that the casino is going to make more. Expects to win, the casino expects to win, oh, sorry, 20 cents each time somebody plays, okay? So let's calculate out our variance for this, see how subtracting is going to affect our variance. Variance. Now with this, right, so this is E of X squared I need to calculate, and I need to then subtract out E of X, quantity squared. So I'm going to do that. This is going to be minus 2 squared, 0.3, plus a minus 1 squared, 0.4, plus 2 squared, 0.2, plus 4 squared, 0.1, and I have to subtract out minus 0.2 squared. Okay, this is my mean squared. This is my E of X, X is squared, E of X squared. Okay, so when I do this, right, and I calculate it all out, I'm going to get, this is equal to 4 minus 0.2 squared, and this is going to equal to, sigma squared is equal to 3.96. Oh, look, it's the same variance that we got before. Subtracting a constant term from each of our individual outcomes had no effect on the variance. Okay. So let's see in the last case, right, where the casino doubles everything, right? So we take the one that we just had, the distribution we just had, and we double everything. It's not 800, it's $8. So minus 4, we lose $2, we gain $4, and we gain $8, not 800, $8. Okay, same probabilities, okay? We want to be able to figure out what's our expected value and our variance. So I'm going to go through the same thing. So our E of X was our mean. I'm going to sum it all up again. So minus 4 times 0.3 plus a minus 2 times 0.4 plus a 4, oops, times 0.2 plus an 8 times 0.1. Okay, when I calculate this out, I get a minus 0.40. This is money. Okay, this means, right, we've doubled, right? We've doubled all of our individual outcomes. So our mean has changed from minus 0.2 to minus 0.4. Okay, so we've doubled our outcomes, we've doubled our mean. Okay, so it's like what we talked about. So this is mu, our new mu is equal to 2 times our old one from the previous case. Okay, so this was equal to 2 times minus 0.2, right? So because we doubled all these values, so we double changed that. Let's talk about our variance, how that's affected things. Okay, so I need to calculate E of X squared and then minus this 0.4 squared. Okay, so I'm going to go minus 4 squared, 0.3, plus minus 2 squared, 0.4, plus 4 squared, 0.2, plus 8 squared, 0.1, and I'm going to subtract out minus 0.4 squared. Okay. Now, when I do this, right, I'm going to get, this was equal to 16 minus 0.4 squared. Okay. When I do this, I get 15.84 equals our new variance. Okay. How does this relate? Let me just show you how it relates. Right, our old variance was 3.96. Okay. So if I take our old variance, which is 3.96, right, so this is our sigma squared old, right, and I multiply it by 2 squared, 3.96 times 4, right, we doubled all of our values, okay, so that's our multiplier 2, right, doubled all of my values, so I square that value, and I'm going to get 15.84, which is equal to our new value here, okay. So we're showing you through an example, okay, how those different properties are actually working. And then we'll sum up with a continuous random variable, just so you can see how things look slightly differently with continuous values. Okay. I'll give you guys a second. There's a lot of numbers in there to write. And I will be posting these later just so you can get a feeling for what's going on. Okay. So example 6, right? Do this. So we have a continuous random variable y. Okay. Let's see. Get this straight. Okay. Yeah. Continuous random variable y with our probability distribution function of 2y. Okay, so that's not so bad, it's linear, from 0 to 1. Okay, and we want to find out what's the standard deviation of 3y plus 2. Remember, standard deviation is related to variance. We take the square root of our variance. Okay, so first off, I need the variance. Okay, so we need to calculate the variance of y. Okay, so I have to calculate that. So I'm going to go, I need my expected value, because I'm going to use that e of y squared minus e of y quantity squared. So I need this expected value first. So I'm going to go from 0 to 1. I'm going to take my probability density function. I'm going to multiply y, 2y, dy. Okay. Now, when I'm going to get 2/3 y cubed, right, because this is 2y squared, so 2/3 y cubed from 0 to 1, which is going to give me a mean or an expected value of y of 2/3. Remember that, we're going to need that when we calculate the rest of the variance. So my e of y squared, okay, I need that for my second portion of my variance calculation, 0 to 1, y squared, 2y, this is actually y like this, dy, okay, so this becomes 2 times y cubed, okay, so when I integrate that, I'm going to get 2 times y to the 4th all over 4, so 1/2 y to the 4th, evaluated from 0 to 1, is going to give me an e of y squared equal to 1/2. That's part of my variance. So my variance of y, which is sigma squared, okay, is going to be e y squared minus e of y quantity squared. So I'm going to plug in, okay, e of y squared we figured out was 1/2 minus 2/3 squared, okay, which is equal to 1/18, which is our sigma squared. That's our variance of y. But we were asked to come up with variance of 3y plus 2. So now I've got this. So if my variance of y is equal to 1 over 18, so let's write that down. The variance of y is equal to 1 over 18. Then the variance of 3y plus 2. We've already said that the plus 2 part's going to have no bearing on changing the variance, but the 3 will. So this is going to become 3 squared times the variance of y. Okay, so that's going to equal to 9 times 1 over 18, which is equal to 1/2. And that's equal to the variance of 3y plus 2. Okay, now that's our variance. We wanted the standard, the question was standard deviation. So let's write that down. Standard deviation is our square root of our variance. (3y plus 2). Okay, so I'm going to take the square root of this value here. So it's going to be square root of 1/2, which is about equal to 0.707. Y plus 2. So be careful. It's not really sigma. Okay, so that's our standard deviation of this here. And you saw in the previous example cases like when I would do 3y plus 2 or 3x plus 2 kinds of things. Okay, what kinds of means that we would need to do that, reasons we would need to do that. Okay, there's one thing I just want to summarize what all these things stand for and what do these things mean. Give you guys a second to finish writing down all these numbers here, and then we'll summarize it, and then we'll be done for today's lecture. Okay, so I wanted to point out, you may have recognized some of the calculus when we were doing the expected values on things. And it may have looked similar to the things that you had done in calculus 2 when you were calculating the moment or the center of mass. Okay, so let's talk about that. We often there's certain types of probability analysis or statistical analysis that uses what we call the method of moments. I'm just going to throw this out there so that you recognize that the terminology when you hear it. I think that there's a second half of this class that's a little bit more advanced. It builds on what we're going to learn here, and then they're going to go into more detail about the method of moments. So the moment, we're going to talk about it as a quantitative measure of the shape of the function. The function meaning the function that's being used to describe our underlying data. Okay, so in physics, we think about our moment as being like our mass is our 0th moment, right? Our center of mass is our first moment. This is what we were calculating when we did the expected value. That's our center of mass. Okay, we have also rotational inertia as our second moment. Okay, so our 0th moment, first moment, second moment. But with probability, these things correspond to different ideas. Probability, distribution. And I'll write, it's our function and values. Okay, so our 0th moment corresponds to the total probability. This is going to sum up to equal to 1, right? The total probability under our distribution, whether it's continuous or discrete, our total probability is equal to 1. So that's our 0th moment, okay? Our first moment is our mean, which is our expected value. I'll write it like this too. You remember when we calculated these values, this is our center of mass. If you remember in calculus 2, you were given some area under a curve. You're asked to find the center of mass. That was x times the function integrated across some range of values. That gave you your center of mass of that area, okay? It's the same calculation that we did when we did the expected value. We said x times our probability function, and we integrated across our range of values that defined our probability function. So our first moment is our mean, and that's our center of mass, essentially. Our second moment is our variance, sigma squared. So it tells us like the spread of the data, right? How variable is our data. Our third moment is what's called skewness. And this basically, I'll write it out as a formula and then I'll write it in words. You don't have to know. We're only talking about things in terms of the 0th, first, and second, but I'm letting you know in probability what measures can use to talk about our data spread. Okay, so our skewness, in terms of a formula, looks like E of x minus mu. This is cubed all over sigma cubed. That's a cube. And what this tells you is how long of a tail. So I've got some kind of a distribution. Do I have a long tail in one direction or a long tail in the other direction? So if my skewness is positive, we have a long tail of our distribution in the positive direction. Positive and negative direction don't mean so much right now. Until we get into normal distributions, you'll know what I'm talking about. Negative means we have a long tail in the negative direction. Okay, so the skewness. So is our data skewed towards one side or the other? Okay, our fourth moment is something called flatness, or what we call kurtosis. There's a lot of words for things, kurtosis. Okay, and this mathematically is set up like E of x minus mu to the fourth all over sigma to the fourth. And this is how flat looking our distribution is, or how peaky, right? So if we have a uniform distribution, it's very flat. Whoops, sorry, I don't think you can see that. Our uniform distribution is a very flat, right? Or something, a distribution that comes up to a point, it looks like this. This is very peaky. Peaky, this is very flat, okay? About different types of distributions, just so you know that these things come into play in a more advanced probability of statistics class, but you may read about this to some degree in your book. Like I said, we're only talking about up to the mean and the variance in our class, but I wanted to throw these out here in terms of how we can use all of this information to help us describe what the data look like. It actually is a pretty powerful tool for helping us to describe things. Okay, so that was chapter 3.5 and 3.6. And I'll have office hours today. If you guys want to talk, the homework assignment for this week was posted online last night. If you want to take a look at it, you're free to come to office hours and ask me questions about that or about other things too. Okay. Have a great day, guys.
Thank you.
Bye-bye.